Hi all, in this video we will see the step up or boost converter. So the step up or boost converter, as its name suggests, gives an output voltage that is always higher than the input voltage. So both the inputs and outputs are in DC. So the figure shows the circuit diagram for boost converter with a power semiconductor switches. We can see that there is an inductor L, two switches S1 and S2, a capacitor, and then the load. In this figure, figure A shows the boost converter with a SPDT switch, that is single pole dual throw switch, single pole and dual throw switch, then an inductor and a capacitor. Now in the second figure, SPDT switch is replaced with two switches S1 and S2. S1 and S2. Then there is an inductor and capacitor. And the figure C, it represents the operative circuit during the period D into Ts. D into Ts means one switch is on, another switch is off. Here S2 is on and S1 is off. S2 is on means S2 is closed. And in the last figure, figure D, it represents the operative circuit during the period 1 minus D into Ts. So D into Ts is the T on. D into Ts is the T on. And 1 minus D into Ts is the T off. So T on and T off are represented by D into Ts and 1 minus D into Ts, where D is the duty cycle. Here, the inductor which is connected to the switch, SPDT switch, or to the pole, the center point is called P. Here the inductor which is connected to the pole is having always a current flow. That is, there is no discontinuity in the current. It is because in either way, whether the switch S1 is on or S2 is on, the current will be conducting through the inductor. So we are saying there is no discontinuity in the current through the inductor. And please note that the inductor is connected between the pole and the input source. Please note that the inductor is connected between the pole and the input source. So the inductor is between the input and the pole. So inductor is connected at the input side. But for the buck converter, inductor was connected after the switch and the capacitor. So it was in the output circuit for buck converter. But for the boost converter, the inductor is connected in the input side. So looking at the figure C, this is the operative circuit during D into Ts, that is during the on time. So during that, S2 is on, S1 is off. Therefore, the pole is connected to the inductor and to the input and to the ground. So the circuit will be completed as shown. And during 1 minus D into Ts period, switch S1 is closed, S2 is open. So the input will travel to the output side. So during this time or during this period, the inductor current cannot change instantaneously. So what happens is the stored energy in the inductor as well as the input current, input signal is being given to the capacitor so that the output voltage is increased. Now the operation of boost converter. The operation of boost converter is analyzed by visualizing the waveforms of various signals of the circuit. Like we discussed in the previous case, here we are considering the voltage across the inductor, current through the inductor, load current, current through the capacitor, input source current, voltage across the switches S1 and S2, and current through the switches S1 and S2. So these are the parameters that we are taking into account for analyzing the operation of boost converter. So this is the waveform which shows the inductor current and inductor voltage and inductor current. So during the d into ts and 1 minus d into ts time is represented here. So during d into ts, S2 is on. Please listen. During d into ts time, S2 is on. Similarly, during 1 minus d into ts, S1 is on. Okay. So when S2 is on, there is a high current, high voltage across the inductor. High voltage across the inductor. Therefore, the inductor current is increasing. So the rate of change of inductor current is VI by L. The current change is equal to VI by L. And when during the 1 minus d into ts time, the inductor voltage drops to minus value. Therefore, the current through the inductor is represented as VI minus VO divided by L. VI minus VO divided by L. Okay, so during the d into ts period, the voltage across the inductor will be Vi minus 0 because this terminal is a negative or ground. So Vi minus voltage at this point will be 0. So therefore, voltage across inductor will be equal to Vi minus 0. Then the current IL is equal to Vi by L. And during the 1 minus d into ts period, the voltage across the inductor is Vi minus Vo because the pole is connected to the output terminal. Therefore, voltage across the inductor is equal to Vi minus Vo, and the current through the inductor is IL, that is equal to Vi minus Vo divided by L, and that is represented in the waveforms. These waveforms represents the current through the capacitor and the current through the switches S2, S1 and voltage across the switches S2 and S1. So in the first case, when the inductor is charging or when S2 is on, when S2 is on, there is no current through the capacitor. When S2 is on, there is no current through the capacitor. So that is the current through the capacitor is represented as negative. And during the second time or 1 minus d into ts time, the capacitor current increases and then starts decreasing because this is provided by the input side and the charge stored in the inductor. So that value is equal to Vi minus Vo divided by L. This is the current through the inductor. The current through the inductor is given to the capacitor itself. Current through the inductor is given to the capacitor. And these are the currents which are going through the switches S1 and S2. So this, when S2 is on, this is the current. So we can relate these currents with the current through the inductor. And then S1 is on, the same current will flow through the switch S2. Then voltage across switches will be also varying with respect to the switching intervals. So during d into ts duration, like we discussed, switch S1 is off and S2 is on. So the voltage VL across the inductor during this time is Vi, which is a DC quantity, because here every voltage is DC, but because of the presence of inductor, there is a small AC component which is not considered. So the current through the inductor is equal to IL, that is equal to 1 by L integral voltage through the inductor into dt. So the voltage through the inductor during dTs is Vi. So we can give that is equal to Vi. 1 by L integral Vi into dt, that is equal to Vi by L integral dt. Because the Vi is taken outside because Vi is a DC quantity. And during 1 minus d into Ts time, switch S1 is on and S2 is off. The voltage VL across the inductor is equal to Vi minus Vo, like we discussed. So in the boost converter, Vo is always greater than Vi, and therefore Vi minus Vo is a negative quantity. So considering that the input-output relationship, that is the considering the voltages during both d into Ts time and 1 minus d into Ts time. Vi into dTs, this is the voltage during d into Ts. Vi, it is the voltage across the inductor during d into Ts time, plus Vi minus Vo, this is the voltage across the inductor during the 1 minus d into t, 1 minus d into Ts time. So considering these values, we can write for the voltage across the inductor, the total voltage across the inductor over a cycle, over a period, will be equal to 0. So that is why we are writing this equation: Vi into dTs plus Vi minus Vo into 1 minus d into Ts. These are the voltages across the inductor during dTs and 1 minus d into Ts, and that is given as 0. So simplifying this equation, simplifying means we have to expand this equation and then simplify for Vo. That is equal to Vi divided by 1 minus d. So this is the input-output relationship. Vo is equal to Vi by 1 minus d. So observing this, the duty ratio d can take values between the closed interval 0 and 1. Observing this, we can see that d will have maximum 1 minus, observing this, we can say that d will have the maximum value which is equal to 1 or less than 1. So whenever the value is less than 1, we have an output voltage which is greater than the input voltage. So this is why the output voltage Vo is always greater than the input voltage, and hence this is called a step up converter or boost converter. Similarly, we can consider Vi into In is equal to Vo into Io. For the input current, expression for input current I in is equal to Io divided by 1 minus d. It is taken from the previous equation where Vo is equal to Vi by 1 minus d. So we have a Vo here and Vi here. We can substitute for that. So we get 1 minus d, and then the remaining part is Io. That is I in is equal to Io divided Io Vo Io. That is I in is equal to Vo Io divided by Vi. That Vo by Vi is equal to 1 by 1 minus d. Now the inductor value or current ripple. So the inductor value is given by Vi into d divided by delta IL into Fs, where Fs is equal to 1 by Ts. So we have to memorize this equation. There is no need of studying the derivation of this equation because it is not mentioned in the syllabus. So, but we have to memorize this equation. The inductor value L is equal to Vi into d divided by delta IL into Fs. So the current ripple is represented as delta into delta IL. Current ripple is represented as delta IL. Therefore, delta IL is equal to Vi into d divided by L into Fs. Or we can write it as delta IL is equal to Vi dTs divided by L. Vi dTs divided by L. Now the capacitor value and the output ripple voltage. So the capacitor value is also calculated by the change in the capacitor charge. Delta Q is equal to C into V. Delta V is the change in voltage across the capacitor. So we are representing that IO into delta dTs, and finally we get the capacitance C is equal to I0 into D divided by delta VO into Fs, where Fs is equal to 1 by Ts. And the output ripple voltage delta VO is equal to I0 into D divided by C into Fs, or we can write delta VO is equal to I0 dTs divided by C. So that is about this lecture. You can clear your doubts during the online class, and thank you so much.